record. Boom. So, are there any questions from last time? This is our class meeting for Friday, the 26th. Any questions on chapter 5 stuff? You can unmute or you can type in the chat. The big takeaway from yesterday is the electron configurations. So yeah, we can go over orbitals again. So basically, you have your nucleus, and then you have the electrons. Yep, we'll do that too. The electrons are out here in electron shells. And the original Bohr model said that there were, orbits around the nucleus. That's what it means by atomic orbitals. It's kind of a leftover term. But this was actually only one of the areas where an electron could be. So in reality, electrons are more like clouds. So if we have our nucleus, our electron could be in a spherical cloud around the nucleus in what's called the s orbital. But in the second orbital, it can be in a cloud like this, in a big sphere, but it can also be in these dumbbells. And what these shapes are basically time lapses of that one little electron kind of bouncing around everywhere. So in the case of the S's, you have two electrons that are kind of bubbling around in here, and then two electrons that are kind of bubbling around in here. But for the P's, that's one electron here, and then one electron here, and then one electron here. Sorry, two electrons in each one of those orbits. So that gives us the different orbitals. Now, I'm not going to attempt to draw the D or the F orbitals because I'm not a very good artist. But the basic idea is that instead of electrons, being a dot that is moving along a path, they're able to just kind of go wherever they want. But if you sit there and you look at the electron over time, you notice that the electron starts to be making that shape. In this case, that would be like the S shape. So this leads us to electron configurations. This is going to tell us where every single one of the electrons are. So in the case of the diagram, the energy diagram, if this is increasing energy, the very bottom here is 1s. And then it takes a little bit more energy for electrons to exist in the 2s. And it takes a little bit more energy than that to exist in the 2p. And each one of these boxes here is representing the shape, S, and the number of orientations that shape has. So S only has one orientation, so it has one box, and P has 3 orientations, so it has 3 boxes. Then we have 3S, and then we have 3P, we get 3 lines. And then we have 4S, and there's a big gap, and instead of 3D being here, did draw the box. Then you have 3D over here. And then you have 4P. Now, why is the d orbital pushed up into the 4th energy level? Well, let's just go through and see what's happening as we're doing electron configurations. If we do the electron configuration of hydrogen, hydrogen has 1 electron. So we take 1 electron there, and we get 1s1. If we have lithium that has 3 electrons, so we get 1s2, just like we did before, and we go like that, and we get 2s1. Then we do beryllium with 4 electrons, and we get 1s2, 2s2. So let's just go ahead and, so the number to the left is what's called the principal quantum number, and that is the energy level. So you can think of it as like terms of like, this is like balloons inside balloons. If this is the nucleus, the 1s is the smallest shell. And then in the 2s, there's this shell, but there's also those p orbitals that are existing in there. And then the 3s encompasses all of that. And then there are the 3p orbitals that are coming out here and doing their thing. And then the 4s encompasses all of that. So the 1, 2, 3, and 4 is telling us how, and what energy level is that electron or electrons. So if we go all the way up here, do we get to a D? So this is scandium right here. We're just going to fill in everything. So what's happening is all of these electrons are down here on the bottom. Now that wouldn't be a big deal if electrons weren't all negative. But because electrons are all negative, this is scandium, they're all going to be starting to push on each other. So instead of the d orbital, again, remember this is an orbital chart showing energy, instead of the d orbital being down here before the 4s, all these negative charges are pushing up on it. And it requires just a little bit more energy to be a 3d than it does to be a 4s. And so that's why when you write the electron configuration of scandium, you get the 3d happening after the 4x. And then you do 3d1. Now, if you're reading the book, there's lots of exceptions going on in the d and the f orbitals. We're just going to assume that everything just kind of fills in. I don't ask you any of the exceptions on the test. I didn't ask any of the exceptions on the quiz, so. Because there are a few exceptions where there's like partially filled orbitals and all that, but we're not going to get into those for the sake of just, you know, high school chemistry that we're trying to crank out in 6 weeks. So yeah, so remember, that's how we're doing the electron configurations if we're using the orbital diagram, okay? If we're not going to use the orbital diagram, we can use a periodic table. Google periodic table. Let's do the SPDF there. SPDF. So if we look at the periodic table can be broken down into these 4 regions on the periodic table, which we can call the S, the P, the D, and the F block. Let's take a snippet and zoom up on this. So if you have your periodic table printed out, or if you want to just look this stuff up, as you can see, the periodic table, if we look at it like this, can be used to write electron configurations. Here we have the S block right here. Right. Here we have the S block over here. And here's the P block, here's the D block, and here's the F block. Okay. So if we're writing the electron configuration of hydrogen, hydrogen is in the first row, in the S block, in the first position. Helium's a bit of an exception because it's over there, but that's because they didn't even know helium existed when they built the periodic table. But it's in the first row, in the S block, in the second position. Lithium has to go through both of these. So we write 1s2. And then it's in the second row, in the S block, in the first position. So using the periodic table to write electron configurations is easy. It's just that you have to remember that it resets. Because as you can see, the D block is in the fourth row, 1, 2, 3, 1, 2, 3, 4. But this is called 3D. And again, that is because of those electron shielding. I like the periodic table method. Reminds me kind of like a battleship or whatever. The problem is with electron configurations is they start to get tedious when they start to do really big ones. Even something, you know, like bromine. Bromine is number 35 on the periodic table. So we have to do 35 electrons. So if we're doing that orbital diagram, we left off at what, 20? 21. So 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. And I didn't even draw, oh no, 35. There we go. 35 is what I was counting to. So there you go. That's a lot of little ticks and stuff to draw. So this makes it a little bit easier to do on some of the longer ones because we just go bromine and we're going to travel through the 2s, so that's 1s2, and we're going to travel through the 2s, so 2s2, and we're going to travel through the 2p, so 2p, and you'll notice there are 6 of these things here, so 6. Then we're going to travel through here, 3s2, and we're going to go through here, 3p6, and we're going to get right there. So not 3p6, we're going to go 3p5. So that's how you can use the periodic table to do electron configurations. The reason why this worked out was a coincidence, as you'll learn today. The periodic table is arranged in columns, which we call groups, of similar properties. So for instance, this first group here is called the alkali metals, and they're all together because they're extremely low melting point metals that are extremely reactive, and they love to form +1 ions. Well, when they were being put together, they were just being put together based on their properties. Well, guess what? Their properties are determined by their electron configuration. And more importantly, the last electrons in the electron configuration, the valence electrons. So you can use the periodic table. Now, say for instance, you have, you know, like iron, it's way down here, and it's a big pain in the butt to do. So rather than writing, you know, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, that's iron, we can abbreviate electron configurations by chopping out the last noble gas. So these are the noble gases in group 18. They weren't known during the formation of the periodic table. And they end the group, or sorry, the period each time. So what we can do is we can take this and we can abbreviate it. So instead of iron being 1s2, 2s2, 2p6, 3s2, 3p6, we can shorten this to just simply writing argon. And then write 4s2, 3d6. And that's in a way you can do that. So is there anyone in particular you'd like me to see do for electron configurations. Now, if you were to Google some of these, again, remember there are exceptions to the rule. A great example of this is manganese. This one you should think is 4s2 3d5, but if you were to look that up online, it would say argon 4s1 3d5 or 3d, yeah, 3d5 or whatever. It's weird. Don't worry about it. We're not going to worry about the exceptions. So chlorine, sure. Chlorine's right there. That was one of the examples we did, but there's chlorine right there. It's number 35. Remember when you do a chemical symbol, one capital letter, one lowercase letter, because if you write Cl, that's carbon and some element L, which if you look on the periodic table, there is no element L. So anyway, so chlorine has 35 electrons. It's right there, or sorry, 17 electrons right here. And so, we were doing bromine before. Chlorine is number 17. So chlorine, I don't know why I did that. Let's go ahead and erase this stuff. Yeah, we can do that right after we do the chlorine one. All right, so chlorine is number 17 on the periodic table. If you're using the orbital diagram, you can just count to 17 and then write what it says, 1s2, 2s2, 2p6, you know, that kind of thing. If we're doing the periodic table here, there's chlorine right there. So chlorine is going to be 1s2, and then 2s2, and then 2p6, and then 3s2, and then right there. So 3p, 1, 2, 3, 4, 5. And then the noble gas abbreviation for this is chlorine is in the third row. So the second row right here is the end. So we're going to abbreviate all of this by just simply writing it neon. And then we're going to go where we left over. We're left over right here. So that's going to be 3s2 and then 3p5. Make sense? All right. So you guys want to see one with a 4f or a 5f. So let's do basically humans' favorite element for thousands of years. Let's do gold. Gold down there, number 79 on the periodic table. So going through there, we get 1s2, and then we get 2s2, and then we get 2p6, and then we get 3s2, then we get 3p6, and we get 4s2. And notice this is 3D, and there's 10 in the D, so 3d10, 4p6, 5s2, 4d, remember, 4d10, 5p6. Now we're going to go down here, 6s2. And remember, this is 5D, and gold is the number 9 here in 5D. But if we write this right now, you'll notice that we should have 79 electrons. And if you add up all these numbers here, because these are the numbers of electrons, 2 and 2 and 6 and 2 and blah, blah. If you add those up, it doesn't add up to 79. Why? Because look at the way we counted. 57 down there then jumped to 72. But where's 58 through 71? And the answer is, it's down here. So instead of writing 5D, we write 4F. And there are 14 in the F block, so we write 14. And then we write 5D9. Now again, that was a big pain in the butt, and I wouldn't ask you to write the complete electron configuration of something way down there. So what we can do is we can take this guy, which just so happens to be xenon, and we can also write this as xenon 6s2 4f14 5d9. Now, another thing you'll see when you go online is they write them backwards. About 15 years ago, there was a shift in writing electron configurations where you write the electrons that leave first at the end. So if we were to Google electron configuration of gold, you'll notice it'll say 4F14, 5D9, 6S2. Now, why does it do that? And see how this is one of the exceptions where they did 5D10, 6S1. And the reason why they write it that way now is, again, the concept of valence electrons, which we'll talk about in today's lecture. But basically, there was a shift to writing it this way years ago to show which were the electrons that were active in the chemistry of that element, or which ones were the valence electrons. So when it comes to gold, the 4F electrons don't do anything, and the 5D electrons do a lot less. And so what's the most active electron? Well, it's going to be the 6s1. So that's why it's written backwards. Another reason why they liked it is because it goes 4, 5, 6. And again, you guys don't need to know that. You can just go ahead and use the way it appears on the periodic table and just count them up from there. If you're super interested in metallic chemistry, you want to be a metallurgist, then you're going to want to learn all these exceptions, but that's not how that's going to be. I don't write the exceptions on the test, so there you go. So just do it this way where you just count up. I just tend to try and give you easier ones like silicone or, you know, arsenic or, you know, magnesium. So that way you can, there's not an exception to that. They're obvious. But the D and the F block do interesting things. All right. So that's electron configurations. So, you ready to talk periodic table? Or you want some more examples? Okay, let's go ahead and jump right into the periodic table. All right. So, periodic table of the elements was designed by a Russian guy. He's got a pretty cool story. If you watch the video I provided from Crash Course, it talks about Mendeleev's story. Pretty devout follower of chemistry and other things. But Mendeleev decided that there was some sort of cool pattern in the way that the atoms arrange themselves. And he spent his life trying to find this pattern. And the modern periodic table is based off of his ideas. And what he came up with was what we call periodic law. And what periodic law is that it says that atoms are periodically similar to each other. That's why it's called the periodic table. Hydrogen is like lithium and sodium and potassium. lithium, but it's not like helium at all. And then it switches back. And so the periodic law states that atoms are periodically similar to each other. And this is occurs as you go from increasing atomic mass. That's what Mendeleev said, because he didn't know about atomic number yet. But as we figured out, we now know atomic number. So here are some examples of what I'm talking about. You can see that the lithium, the sodium, the potassium were all metals. Same thing with the beryllium, the magnesium, the calcium. They were all metals. And they produced bases when reacting with oxygen. And then the alkaline earth metals, which are beryllium, magnesium, produced basic to kind of neutral. And then you'll notice as soon as we hit the P block, we start seeing nonmetals, but we also start seeing acidic oxides. And once we get over there to the fluorines, then we're looking at just straight up acidic as it is. So that was some of the stuff that they were looking at. So why Mendeleev gets kind of his name on the periodic table is because he was able to predict the presence of gallium and germanium. And he didn't purify them or even identify them. He just said, these are the stats they should have, as you can see on the table there. And when someone actually purified them, he was pretty much dead on, which is pretty cool. All right. So basically, he was putting them together in terms of their similar properties. But what it actually was their electron configuration. And more specifically, the last electrons in their electron configuration, the valence electrons. So if we look at the electron configurations of lithium, sodium, potassium, rubidium, cesium, and francium, all of their electron configurations will end in S1. The valence electrons are the final S and P electrons of every single atom. So the alkali metals, the first group on the periodic table, group 1A or group 1, is similar because of this one valence electron similarity. Now again, Mendeleev put them together simply because their properties all matched, but it turns out their properties were caused by the electrons. If we look at the noble gases, which is group 8A or group 18 on the periodic table, also have a similarity in their electron configurations. The exception to this is helium with its 1s2, but basically their similarity is that their shell, their orbital shell, is full. The first principal quantum number, the first energy shell, only has 2 spots, so helium fills it, and therefore it behaves like a noble gas. But every other one after that, neon, argon, krypton, xenon, radon, those guys all have 2s2, 2p6 as their end to their electron configuration. And so that's why they're all noble gases. Mendeleev didn't know about the noble gases at the end. So when we talked about ions, we talked about how some of the ions want to form positive ions and some want to form negative ions. And we said that metals tend to form positive and nonmetals want to form negative. And the reason for this is because of the filling of their valence shell. They want to fill it up. So the metals are easier when they lose their electrons, and the nonmetals are easier when they gain. And so we'll get into that. The rule is 8 valence electrons. We're going to talk more about this when we get to chapter 7. We're going to keep going to periodic table stuff. So If we look at the periodic table then, we're going to get back to trends in a second. I don't want that anymore. I want periodic table. Let's just do a regular periodic table. If you look at the periodic table that I gave you guys, it color codes things based off of kind of like their elemental groups. Is a good example. So right here in our first group on the periodic table, group 1 or 1A, this group is called the alkali metals. They're all very soft metals. They're all very reactive. They like to form +1 ions. These guys right here are called the alkaline earth metals. They are softer than other metals, but not that soft. They are low melting point, but not as low as the alkali metals. And they are reactive, but not as reactive as the alkali metals. And they like to form +2 ions. The D and the F block are a little weird. They like to do weird things. But the reason why the D and the F block are kind of blocked together here as what's called the transition metals is because they're very, very similar. They're all metals. They have high melting points with the exception of things like mercury here. And they are metallic. They conduct electricity. They like to form positive ions. But they're inconsistent in how positive they want to be. Some are +1 for obvious reasons. Some are +3. Some are +2. Some are +6. So it's all over the place. This group right here, group 13 or 3A, is called the boron group, where it has one what we call non-metal. However, the staircase here that you see is there to show the separation between the non-metals and the metals. And some of these atoms that touch the staircase are actually what we like to call metalloids. So aluminum is so metallic in character that we just call it a metal. Boron, for instance, is also very, very non-metal in character, so we tend not to call that a metalloid either. But it really depends on your periodic table. Some will call boron a metalloid, some won't. The difference between metals and non-metals is metals tend to lose electrons, they like to be conductive, they're very malleable, and they usually have higher melting points. Non-metals are very, very low melting points to the point where most of them are gases or can be melted with, just a simple little flame. And they love to gain electrons to become stable. Silicon and germanium are great examples of metalloids. Arsenic and antimony are great examples of metalloids. Tellurium is a good example of a metalloid. Polonium, it really depends on your periodic table. Some will say metalloid, some won't. Polonium is very radioactive. You have to isolate it. And so it can behave mostly like a metal, but there are non-metal properties to it. And then astatine is so rare that it basically is impossible to say what it would be. It is a halogen, which is group 17 here, we'll talk about in a second. So it's anticipated to be basically non-metal and not be metalloid, but there's so little of it on the planet that if you gathered all of it in one place, it would be less than a gram. So it's pretty rare stuff. So the boron group has basically a non-metal and a bunch of metals in it. And then we have the carbon group. Carbon and silicon, very similar to each other in terms of their properties, but silicon has that metalloid properties that make it so awesome for computers, which is how we're talking today, which is pretty cool. And then these guys become metals. And the carbon group contains two very, very old and well-known metals, tin and lead. So kind of cool to think that lead is very similar to carbon in some ways. Then you have the nitrogen group. Nitrogen and phosphorus and arsenic very similar in their properties. Arsenic behaving in some metalloid type of ways. Then you have antimony and bismuth. If you ever taken Pepto-Bismol, there's bismuth right there. Then you have the oxygen group, oxygen, sulfur, very similar to each other, selenium and tellurium. Selenium being more solid than these other guys, and then tellurium having kind of those metalloid characteristics. And then finally the halogens. The halogens are very similar to each other. They're called halogens, or halo, because they tend to be gases or liquids that have cool colors on them in their pure forms. So that's why they're called the halogens. They are very reactive, some of the most reactive elements on the periodic table. Fluorine is considered the most reactive, and that's because they're all one electron away becoming a noble gas, and so they want to gain that electron very quickly. So that's why they form -1 ions. The oxygen group tends to form -2, and the nitrogen group tends to form -3. But again, this staircase separates metal from non-metal, so these guys tend to break that rule down here. And then finally, we have the noble gases. Noble gases are the called the noble gases because they didn't react with anything, so they were considered nobles because they were above everyone else and wouldn't interact with anyone else. So that's that. And then the D block is called the transition metals, and the F block is sometimes called the intertransition metals or the rare earth elements down here. But basically what we call them in chemistry is the lanthanide series, because it starts with lanthanide, and the actinide series, or the actinoid series in this case, because it starts with actinium. Lanthanum and actinium are number 57 and 89. Sometimes you see them down here, sometimes you don't. So if we go back over to our periodic table, come on. There we go. You'll notice that if you go to different periodic tables, there's lanthanum and actinium inside of the D and the F, or sorry, the F block. And then if you go to the one we're looking at, or this one here, you'll notice it puts them up there. So it's a debate out there in terms of what is right here in the 5D1 and the 6D1 spot. Is it lanthanum and actinium, or is it lutetium and lawrencium? Lutetium, I should say. Are those guys there, or are these guys there? And so it's up to the periodic table. This periodic table, as you can see, this is the one I posted for you. They took this is the most modern periodic table I found. They have taken the kind of neutral route and basically put both of them down here and just left this blank. That's good, but it's also not great for electron configurations because you want to put 15 down here because there's 15. So either way. So those are the groups on the periodic table. You can read more about it. So then what are the trends we can see on the periodic table? Well, the size of an atom is based off of its electron cloud. So the bigger the electron cloud, or the smaller the electron cloud, the bigger the atom or the smaller the atom. So if we look at the periodic table, the larger your electron cloud, the bigger you are. So as we go down the periodic table, the atomic radii gets bigger. But what's weird is we go from left to right. Hydrogen, with only one electron and one proton, is actually larger than helium with 2 electrons and 2 protons. And what's the reason for this? The reason is that the protons are not in a new shell, so their power is felt by all of the electrons. And because there's twice as much power, it can pull those electrons closer together. So that's why it gets smaller as you go from left to right. And again, there are some exceptions here, but we're just going to say the general trend is bigger as you go down, smaller as you go across. This is caused by electron shielding, which we'll talk about in a second. Effective nuclear charge, same idea. This is just kind of getting into it. So here's another way to look at atomic radii. It's just a graph of it. And as you can see, we go smaller, but then as we go down the periodic, down a period or a group, or sorry, down a group, we get bigger. And then it starts to get smaller again. You can see there's a little blip in there. But again, the general trend is it's smaller as we go across period 2. But then when we go down to period 3, we get bigger again, and then it happens. And then here's period 4. And then you'll notice how the transition metals are doing exactly what they're supposed to, but do little spikes again and then goes up. Again, that's just a slight little example of the exception to the rule, but against the general trend. And on the test, I tend not to ask you like, what's bigger, this guy or this guy? Because the trend would tell you that this guy should be smaller than this guy, but in reality, it's just slightly bigger. So don't worry about those little exceptions to the rule there. All right. These are some practice problems if you want to do that. And you can see the different exceptions to the electron configurations. This one's like an entire book in PDF form. That's why we're skipping most of it. All right. So most of the atoms on the periodic table don't really want to exist as their atomic form. They want to switch to their ionic form. They want to gain or lose electrons. And so talking about their ionic size is a little bit more appropriate. So if we look at what we call the representative elements, which are the S and the P blocks, you'll notice that the S tends to like to form positive, and then the beginning of the P's tend to form positive. But as soon as we get to group 4A, it switches over to trying to be negative. So this is going to cause two different things to happen. So positive ions, because they're losing electrons, are actually going to get smaller than their neutral counterparts. But the trend is going to still be the same. They're still going to get bigger as they go down and smaller as they go across. However, if we look at the periodic table, though, once we get over to the negative ions are going to be bigger than their neutral counterparts. So what this means is that when we look at the periodic table, no, it didn't do it. If we look at the periodic table's overall trend, we're going to see that I have a better picture. Hold on. All right, chemistry. This would be unit 4. Nope. Nope. Unit 2. There we go. Where did it go? Weird. Not a really good picture. Boo, boo, boo. Boop, 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 boop. There we go. So if we look at this table here, the periodic table, we can see both the neutral and the ionic radiuses. And as you can see, the positive ones, which are the green dots, are much smaller than their neutral counterparts, which are these orange dots. So, don't know why there's a cursor there. So anyway, as you can see, the trend is still the same with the positive ones. But once we hit the staircase, they switch to becoming negative. So negatives are always bigger than positives. But the trend is still the same. They still get smaller as they go across and larger as they go down. We'll just use this one. It's just kind of, well, that's fine. use the one you have. So then we have ionization energy. And ionization energy is important when we look at atoms because we're talking about how much energy does it take for them to lose electrons. Because it was very easy for us to make electrons get kicked out of things. We just hit them with X-rays. So we could use the amount of X-ray we hit an atom with before it would start shooting electrons off of it to understand its ability to ionize. So ionization energy is also an important trend when we talk about reactivity and when we talk about the bonds it wants to form and that kind of stuff. So as you can see here on this graph, anything that usually wants to be a positive ion is going to have low ionization energy. But as soon as you get to the things that want to be negative ions on the right side of the periodic table, or the noble gases, which don't want to be ions at all, they will have very, very high ionization energies. And so the trend is a general increase as we go across the periodic table and a decrease as we go down the periodic table. So here is a little graph of that. As you can see, increase as we're going across and a decrease as we're going down. These are examples you can do. All right. Successive ionization energy, blah, 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 blah. Electron affinity is the same thing for our purposes as what's called electronegativity. So we're just kind of skip electron affinity, but you can read about it if you want. Metallic character, we're not really going to get into, so don't worry about that. But it's like how metallic something is. And that really, this kind of thing shows you in the periodic table the metals, the metalloids, and the nonmetals. You can see that things are more metallic as you go down and less metallic as you go across. Not important. We're not going to get into that. What we are going to get into is electronegativity, which this one doesn't have a lot of information on. So let's just go ahead and jump over to this one. Here's another cool graph of ionization energy. Kind of shows you all the ones on the periodic table there. So then what is electronegativity? Electronegativity is the measure of how much the atom wants electrons in a bond. So how much is it going to try and pull on those electrons? Think about it as the big tug of war. Who is the strongest in a tug of war and who's the weakest when it comes to electrons? And electronegativity is important because it's going to determine most of what is going to be taking place in bonding. So when we look at something like sodium chloride, table salt, why is sodium chloride so stable? And the answer is because sodium wants to be a positive ion, chlorine wants to be a negative ion, and when they get together, their electronegativity difference is so large that chlorine can go ahead and take the electron that sodium has, it can ionize it, and therefore now they can stick to each other. When we look at something like oxygen that we breathe, oxygen is a high electronegativity, but if it's bound with another oxygen, then their electronegativity difference is basically nothing. But because the high electronegativity of oxygen, if you put that oxygen molecule next to something else, it's going to want to react with it. Same thing with fluorine. So you can think of electronegativity as the desire for electrons. That's why I said electron affinity and electronegativity are very similar to each other, but we're just going to concentrate on electronegativity, because of its bonding properties that we're going to talk more about in the next unit. So these are some general trends you can do on the periodic table. Again, the videos that are on, it kind of sums everything up. The videos that I have provided for you kind of sum everything up we talked about today in much shorter parts, 15 minutes, 10 minutes, 5 minutes. Professor Dave does a good job of explaining everything. If you go to the module down here, he explains the three most important ones that I put on the exam. So if you go down to just periodic trends right there, This video by Professor Dave is a good video. I don't know why it's not loading. That's periodic table. Oh, download it. Huh, why isn't that working? Anyway, well, if you click, if it's not going to load inside, yeah, that's probably because I have ad blocker on, as you can see. If it doesn't load in the window, you can click right there and it'll just open it up in a new tab. But anyway, Professor Dave has a good explanation of periodic trends if you want to watch that on top of what we talked about today. All right, so that's everything that is in chapter 6. That's everything for this unit. So the quiz is up. I posted it last night. I made sure it published, so you can go on and check that out. You can work through the worksheets. I'm available all day if you want to shoot me questions. Make sure that you're not sending it to the R. Sullivan at Claremont, because that is not a Gmail account that I have control of. They just set that out in an emergency to try and get us onto the CHS canvas because Citrus still doesn't have their stuff going yet. And at this point, because we're basically done with 2 units, I'm probably just going to keep everything on this and just transfer it over there, and you won't have to do anything over there for this semester if they are still going to be slow about getting you guys on there. So that is today's session. Any questions? All right, then, kiddos, we're going to hit step record. We're going to have to do a little editing on this one.